theorem. So the first step was to find an Eisenstein series whose constant term is related to the L function of interest. I mean, what you can really think of this as finding some very special automorphic form that's somehow related to the L function of interest. In this case, that automorphic form happens to be an Eisenstein series, but the same strategy can actually work with other kinds of automorphic forms. So it was find or construct. This isn't going to be exactly how I stated it before. In this case, a p-adic family of Eisenstein series with constant term or terms divisible by the L function, or possibly the p-adic L function if we're working at p-adic families. L functions, L values of interest. And then one crucial step in carrying this out in general is then and show that the Eisenstein series is prime to the L function, which can be interpreted as saying that there's some Fourier coefficient that's not divisible by p, for instance. It's a unit, so that when you look at everything modulo a divisor of the L function, that your Eisenstein series isn't trivial. So that's what I've mostly been talking about. Well, at least in the last lecture, this is what I was sort of describing as the strategy for producing these Eisenstein series with constant terms that were related to the L function of interest. In this case, GL2 L functions twisted by Hecke characters. Then the second step in the strategy is to show that the Eisenstein series is congruent to cuspidal, possibly family of the forms modulo the constant terms, or modulo the L values. So then the constant term goes away. I'm not saying a whole lot about this. I did this very explicitly in the case of Dirichlet L series, and we were working with Eisenstein series on GL2. And you can do very similar things in general. Then the third part is to exploit the Galois representations associated with cusp forms together with these congruences. To construct elements or subgroups of Sommer groups. And so I'm going to forget about part two. What I want to talk a little bit about today is this third part in the context of GL2 L functions. So what we maybe forgetting about p-adic families for the moment. So we start off maybe with some weight k ordinary. They'll come up later in the arguments. Eigenform. So maybe they're the p or the t. And then we gave ourselves an auxiliary imaginary quadratic field. and maybe a finite order Hecke character. Character of K, and what we're interested in is sort of L functions of F twisted by chi. So a base change of F to the CM field twisted by chi, if you like, or the Rankine product of F with the weight 1 CM form associated with chi, and at some point. So to construct the Eisenstein series in general, there's an auxiliary character that one has to throw in, and then this is going to be again a character of, maybe I should think of these now as of the Adels, cross, such that the infinity type of C is just z to the minus k, where this is the same k as the weight. And if we restrict to the Adels of Q embedded inside here, that this is just essentially the character of F. It's not going to quite be that with this. And then the norm character to the minus k, sorry. Minus k, and that's consistent with this infinity type infinity. And the reason for this is that F together with psi will define a representation on a unitary group. And since we're moving over to the unitary group. And then maybe we'll carry around a finite set of primes. And to make our life easiest, we'll assume that it contains all the primes that divide P and M, and the discriminant of the field K, and say if the conductors of psi and the conductors of chi. Properly speaking, these are ideals, and we take the norms, but clear what I mean. And to this data, we define an Eisenstein series, and we do this by associating. Well, first, we'll take pi to be the cuspidal automorphic representation associated to F, such that L pi of S minus a half. So here's my normalization. Then you can check that the central character is just the central character of F, and then this to the minus k. So that's the same as the restriction of this psi. So then that means that pi together with psi, these define a cuspidal representation of GU11, this group that I defined before, because this was just GL2 with its center extended by K cross. And so all we have a representation pi on GL2, and we just need to extend it to the center, and we can do that with psi because of this compatibility. So we'll call this pi sub psi. And then I'm going to define an auxiliary character, which is tau is going to be psi twisted by the chi minus 1. Actually, I suspect this is going to come back to haunt me, and I should probably take the conjugate character of chi, but we'll find out as we go along. And then, if one looks at the induced representation from the Klingen parabolic, of U22 to GU22. So this was a parabolic I defined that had Levy that was GU11 cross K cross. So to define a cusp form on it, we need or any representation, we need a representation of GU11 and a representation of a K cross. And so I'm going to take pi and tau. So pi sub psi and tau. And then probably I'll take the modulus character, and I'll put it to the 3/2 with what I've chosen here. And this is unitary induction. If I did non-unitary induction, then I could get rid of this. Well, I guess it's really the modulus character to the 1/2. I could get rid of that 1/2, but and then what happens is we can find an F in here, some section, such that the associated Eisenstein series, EF of G, this is our Eisenstein series on U22, is holomorphic of scalar weight K. So it's a holomorphic Hermitian modular form of scalar weight K. So you have to make the appropriate choices of this for this F, but it can be done. And what I sort of sketched last week is how one could get sort of the right section and the right Eisenstein series really just by taking very simple Eisenstein series on U33 and pulling back to an embedded U11 cross U22, integrate against a form coming from this representation, and then what resulted was a nice holomorphic form associated to some section. And one could vary that construction p-adically to get those p-adic families, and one could see from the construction what the constant terms were, and they were related to the doubling integrals, which gave these L functions. All right. So then, forgetting about p-adic families, though, and just sort of looking at this sort of case, suppose that we could produce a cusp form that was congruent to this Eisenstein series, modulo, say, the constant term. And then what would we extract from that is we would try to extract that, in fact, what we have is a congruence between the Hecke eigenvalues of that cuspidal representation and the Hecke eigenvalues of the Eisenstein series. And that's why one needs some Fourier coefficient to not vanish on the Eisenstein series, among other reasons. And then, so then, having that congruence on the level of Hecke eigenvalues will give us some information about the residual representation of the Galois representation associated to the cusp form. So maybe we had to figure out what do we have about Galois representations and what information we can extract by that. So here's maybe a little bit of information about this Eisenstein series. So if I called this big induced representation capital pi, and we pretended that it was irreducible, then we could define an L function to it. And certainly, it's unramified away from the sets in sigma, so we could always take the n, in fact, irreducible away from those. So we can certainly talk about the L function of pi. But what do I mean by that? What I'm going to mean is that we take a U22 constituent, say pi sub 0. So this is going to be some irreducible U22 constituent of pi. So I define things on these similitude groups. Now I'm going to restrict to the unitary group. Talk about it. I can take its formal base change to GL4. Just take the base change away from pi. That makes sense, certainly, if I stay away from the places in sigma. I know how to talk about the base change locally, because everything's unramified. And look at that. And I'm going to twist by the central character of the representation capital pi, which is a Hecke character. But I'm going to twist by its conjugate. Okay, so that's going to be the base change. And what that turns out to be, in this case, if one works it out, it it turns out to be, for this case, and this is I'll have to explain some of this notation, I guess. So the superscript C always means I'm sort of composing with the complex conjugation action on K for a Hecke character. The prime means, now these are L functions of Dirichlet characters of K, of Hecke characters. But what I mean here is I take the inverse character of chi. So chi is finite, so I can just take the complex conjugate of its values. The prime means that I restrict it to the adels of Q, thinking of it as giving a Dirichlet character over Q, which I then get as a Dirichlet character over, or a Hecke character over C by composing with the norm. So one could also think of this as, so chi bar prime is chi inverse restricted to the adels of Q cross. I guess since we don't use it too much, we could have just written as, what it really is chi inverse C, I think. Yes? Pi 0 is essentially arbitrary in this case. Yeah. These are restricting away from sets where there's going to be a problem. Yeah, the primes where that might be a problem. So it turns out to be that. All right, so that's something to keep in mind. So what's it? So now, why is this important? So if we look at the Galois representations, first of all, this is encoding the Hecke eigenvalues of this of pi, more or less. This L function is encoding those eigenvalues. So the Galois representation associated to cuspidal automorphic reps of GU22 are the following. I mean, should behave like the following. So if we have, so now I'm going to, let's get some next. Okay, sigma. So sigma is supposed to be a cuspidal automorphic representation of GU22 with sigma infinity in the discrete series. Then you sort of expect that there exists a four-dimensional Galois representation. So this would be GL4 into Q P bar. Such that if sigma contains all those primes L that divide P, the discriminant of K, and all the places where pi is or sigma, sorry, is not unramified, then the L function of this Galois representation should just be the L function of sigma, so S minus 3/2. And what is this? This, by definition, is going to be similar as before. It would be the L sigma of a base change of some sigma 0, and then twisted by the conjugate of the central character. And so then it'll be evaluated at s minus 3 halves. So the minus 3 halves is sort of the geometric normalization of things. So that's really an s minus a 4 minus 1 over 2. And one would expect that if p does not divide the discriminant of k, and pi p is unramified, then rho sigma restricted to a decomposition group at any prime that divides p of k is crystalline, and the eigenvalues of the crystalline Frobenius is the associated name modular are in fact given by the parameters that show up for the L factor that one would expect here. I'm not going to write that down. So in particular, this would say that if we were in this situation where p doesn't divide the discriminant of k and pi or sigma, sorry, it's still sigma of p is ordinary, then the Galois representation is ordinary. So that's and you understand what the characters are on the diagonal. So So ordinary would imply, the Galois representation being ordinary means in particular that it's sort of upper triangular.
Chris,
Yes?
do you require the image of Galois group inside some GU to
No. I'm not making any claims about that. So.
But it's supposed or expect or...
I mean, so this already implies some conjugate self-duality, and that's whatever, and that should be enough. So now I should say about this is known. So sort of a lot is known about the p-adic Galois representations associated to representations of unitary groups. However, mostly that comes from looking at the cohomology of a Shimura variety, which is sort of a un minus 1 at one place and a un to the d minus 1 like this, for some totally real field D. And it certainly helps to know that this D can be taken larger than 1. And this is the degree of the D is the degree of the totally real field. So if we're over Q, this isn't there. And you can still say a lot now about this situation. But we're actually not in that situation anyway, because we're in the U2 situation. So the first thing one would want to do to get a 4-dimensional representation, so here n would be 4, we would want to move to a group like that. But unfortunately, the current technology with transferring between forms of unitary groups doesn't allow us to do this if we're over Q. Although, I mean, there's certainly no conceptual obstruction to doing so. It's just a matter of stabilizing all the right trace formulas, I think. And then once one had that, you'd be a little bit closer, but there's still, I shouldn't have erased it, there still would be a problem with analyzing perhaps the cohomology of this Shimura variety. At least it's not sufficiently described for the purposes of this theorem. So, but one can combine what is known with some analytic arguments to prove. So this is known if we're in a regular discrete series. So what this can be thought of as meaning is that in terms of the cohomology of a Shimura variety, the local system, which is a representation of the group G, in this case GU22, is a regular algebraic representation. So in the case of GL2, this would mean your weight's bigger than 2. It's a little more restrictive here. So this is known at phi infinity as a regular discrete series. Unfortunately, so far I've been talking about holomorphic forms of scalar weight k, and these are not regular discrete series. And so one has to, but we can get away with that a little bit more because we can exploit the ordinarity at the prime p to put ourselves into a family where you have a dense set of points that are in fact correspond to weights that are regular discrete series, and then you can get what one needs there. You don't really get the crystallinity; you get the ordinary condition possibly at those weights, and then I'm requiring that p split in k for this. That's the context in which the Hida theory has been most fully written out. So maybe what I should say about this for the moment is this combines, the proof of this combines results of Morel, Sagushin, and and analytic results about L values, L functions, and gamma factors for unitary groups, which are also defined through the doubling method. So I can sketch that later if there's interest. I just want to actually use it. So if you forget about cuspidal, then this sort of just tells us what, in this spirit, then the Galois representation that we would expect to have associated to our Eisenstein series is supposed to have this compatibility with the L function. We know the L function, so we can sort of see what the Galois representation for the Eisenstein series should be. So the Galois representation for the Eisenstein series. So we have to shift by a minus 3/2. That's an s minus 2, s minus 3, and an s minus k. So those are pretty reasonable points. And so we would have the Galois representation associated to f. We'd be twisting it by the Galois representation associated to these Hecke characters, which I'm going to write as the Hecke characters. These are all algebraic Hecke characters, and so they have associated p-adic Galois representations. So we'd be twisting by psi of c. And then the shift by minus 2 was just the cyclotomic character to the minus 2. Remember, I'm taking geometric normalization. So that's one piece of the Galois representation. The next piece would be psi of c minus a 3 now, so we have an epsilon to the minus 3. And the third part, so we have these Dirichlet characters, Hecke character, and then an s minus k. So we have chi prime of f, psi of c, epsilon to the minus k. So there's a two-dimensional piece and two characters. And actually, the first thing to note is that this psi that we introduced to define the Eisenstein series seems completely superfluous. I mean, we're just twisting the whole representation by psi, or rather, the conjugate of psi. So in terms of the ratios of any two pieces, it's not playing a part. So it really is just an auxiliary character that's thrown in there to sort of move to the unitary group. We can even we like, write down, well, so we could twist away the psi of c if we wanted, but let's leave it in there for now. That might make life even more complicated. So now, so if we had managed to produce some eigenform that was congruent to our Eisenstein series and then conclude that that was actually giving us congruences about the eigenvalues of the cusp form and the eigenvalues of the Eisenstein series. So if the eigenvalues of sigma, which is our cuspidal representation of U22, are congruent to those of pi, i.e. the Eisenstein series, so that's capital pi, then we see that what we have is that the residual representation associated to pi has semi-simplification given by this. Maybe I should have given that a name. So let's call that rho of capital pi. So that's just rho of capital pi residually. So if this representation were I mean, if the image of rho sigma were large, then we could hope to follow the same strategy of ribbon and get extensions between pieces of the residual representation. So what we really might think of is that we have that rho sigma bar looks like, so down below, I'll put this one down here. So there's a psi c, and then in the middle we've got rho of f twisted by chi minus c, psi c epsilon minus 2, and we have chi minus 1, chi bar prime, chi f, psi of c epsilon minus k. And what we would like is, as I said, so if the image were quite large, then we would start to have this. This wouldn't be fully reducible necessarily. We could choose a lattice where it wasn't fully reducible, and we would start to fill out these corners. If we could do that, and that would be great, because if you look at what this is, so this is what this extension is. This would give us something in H1k of rho of f chi minus c. Well, the psi c's cancel, and so I'm left with epsilon to just epsilon. And how does this relate to the values that were showing up in our Selmer group, or the Galois action in the Selmer group? So I could put in the dual here, and then I would have chi of f epsilon to the 1 minus k, so that's rho of f, just twisting. And then we'd have chi of c and another epsilon, so we'd have a 2 minus k there. And so that's what we were getting. We were getting epsilon to the 2 minus k and some Hecke character, and I guess then I have this finite order Hecke character related to f, and that had to do with our normalizations. But if you remember, this omega to the 2 minus k was coming up, and that was whenever we were in this Heda family of weight k and in the p-adic L function, and so that's chi of f actually belongs there. And so this is the kind of cohomology group. Group showing that we looked at when defining the Selmer groups. So this is exactly, so what we want are extensions like this. And so it's certainly true that if the image of rho were, say, irreducible, then I could choose a lattice whose reduction has any one of the three pieces of the residual representation that I want. But I can't always force the order of what else shows up here. So you could conceivably have reversed the order of these two, and instead of finding an extension in this group, you found an extension in these, between these two characters. And then you have to analyze that extension. That's related to, really to an extension of some Dirichlet characters. That's a Dirichlet character, that's a Dirichlet character, and these chi's cancel. And so it comes back down to what we know about Selmer groups for characters. And so one can, under the hypotheses, for example, that were stated in the theorems and the main results, they could exclude this case. So indeed, you force this kind of extension. But what about knowing that the image is large? Well, what can the image be? This image. So there would be maybe three possibilities where one of the running hypotheses through the results was that the F was residually irreducible. So this is residually a two-dimensional representation, and so you have to have at least a two-dimensional piece here. So either your rho 1 plus rho 2, say, with the dimension of rho I being 2, say rho 1 being conjugate to rho f, and so chi minus c psi c f sum minus 2, and rho 2 being residually the sum of two characters, or it could be irreducible, or it could be some rho plus running out of theta, where this is three-dimensional and this is one-dimensional. And those are our three possibilities. This we can immediately exclude by the self-duality conditions. Being conjugate, this character would have to reduce to one of these characters, and it doesn't work out. So this is easy to deal with. Irreducible is what we want, so we're left with dealing with this possibility, and this is something that can come up. There are indeed cusp forms on unitary, in this case on GU22, whose associated Galois representation would indeed be the sum of two two-dimensional representations. They would be endoscopic forms. I mean, actually, there would be Galois representations like this, which are also endoscopic, but they wouldn't reduce to something like that. So what would happen is that if we can exploit the same argument that we made to sort of say that in the ideal situation we would have this extension here, because if the Galois representation were the sum of these two two-dimensional representations, then this one's reducing to a sum of two characters. And so we use it to construct an extension between those two characters. But we're, again, as we said before, we put ourselves in a situation where those extensions don't exist. So this goes away as well. And so in fact, in the situations that arise under the hypotheses of the main theorem, this doesn't happen.
You're ruling out extensions mod p or something.
Here, yeah, I'm giving the argument that we rule it out mod p. There, I'm wanting to rule it out modulo a prime in the IWASAWA algebra. But if it already doesn't exist mod b, then it can't exist.
Right, but in the second case, you're ruling out
This.
mod p that you.
Oh, and both of these. So I'm ruling out both. I'm ruling out this case by mod p considerations.
Yeah. Whereas previously you were ruling out characteristics.
Oh, sorry. No, this is all mod p stuff. This is all modulo mod p, and this should be mod p as well. I'm just keeping.
Does modulo p also restrict to the local Galois group or the whole Galois group?
So you're asking what would be the shape of this restricted to the local Galois group?
Does it restrict to the local Galois group or the whole Galois?
This is for the whole Galois group, yeah. But only mod p. When you already you know that when you restrict to the whole Galois group that this is, this is ordinary in this setup, and that allows you to actually say that these classes are unramified where they're supposed to be unramified, or have the right properties of p. So the Selmer property at the primes that divide p come from the ordinarity of rho sigma restricted to the decomposition groups above p. So it's actually quite easy to check. So this is sort of a sketch of how one would run the argument in this context that gave the converse to Herbrandt's theorem, producing extensions related to say, the vanishing of an L function. To prove the main result stated that relates the order of vanishing, or relates the p-adic L function to the order of the Selmer group is essentially the same. One just argues where you've replaced sigma and pi with the p-adic families. It's not, there's nothing really different about that argument except there's more notation, right? Of course, one wants more than just modulo p. One would want sort of some information about modulo powers of p. But then the modification needed for that I already indicated when I explained how one could get that the power of p that divides the value of the Riemann zeta function actually divided the order of the appropriate Selmer group. So the only new feature in this argument was the fact that whereas in the GL2 case, one has a two-dimensional representation and you just have two characters in the residual representation, and so there's really no ambiguity about the extensions that you might construct. Here you've got three pieces to the representation, and so you have to take a little bit of care to make sure that you get the right representation that you want. Beyond that, this argument can be done in great generality, and the real difficulty, I would say, in the whole proof is back in this part. Here, this is where all the difficulty was in showing that when you have an Eisenstein series and its constant term is essentially the L value, that there's some other Fourier coefficient that's prime to the L value. And unlike in the GL2 case where you essentially get this for free, this requires work, and that's where the work was. So I can stop there unless people want to hear anything about this, which is the existence of these Galois representations, but it sort of seems like another topic.
Thank you.